So for our next thing here, we have a little task for you all to do if you're watching this later. Find the sum of the integers from 1 to 100. So add up all the whole numbers going from 1 to 100. We'll wait. But spoilers, there's going to be a shortcut for this. So this is actually a classic old problem. And one of kind of the fundamental things in this sigma summation notation. This is a little story that I like to call the Legend of Gauss. Okay, Legend of Little Gauss. All right, so Gauss was a mathematician back in the day. Um, and the legend has it, and this is, I don't know if this has been confirmed, by the way. This is like a mathematical fairy tale type of thing. Um, but the story has it. Yeah, someone in the chat here remembers Gauss. Hey, yeah, Gauss did a lot for mathematics. He's a pretty cool historical figure. But this particular legend has it that little Gauss was a child in school, and his teacher had just had it with the class one day, like bunch of little kids going nuts, wouldn't sit still, that type of thing. And so the teacher got mad and said, okay, everybody just sit down, be quiet, and add up all the numbers from 1 to 100. And you can't talk until you're done. And okay, so all the little students get out their little pencils and paper and they start adding up all the numbers, and it's taking a long time. But then after just a couple short minutes here comes little Gauss up to the teacher, and he has the right answer. And the teacher says, how did you and Gauss didn't actually have to add up every single number here. He used a very clever shortcut. And so we are going to look at his shortcut here. In terms of sigma notation, here's what the teacher was asking the kids to do. Start from 1 and go to 100 and add up all those numbers. So the summation from k equals 1 to 100, and the formula is just k. So that would be like, yeah, take 1 plus 2 plus 3 and keep going, add it up, kids, all the way to 99 and 100. And yeah, someone has heard the legend here. It was something about 2 groups. Yes, it was. So what Gauss did was he split the numbers from 1 to 100 into 2 groups. He said, okay, I'm going to add up 1 plus 2 plus 3 plus all these numbers. But look, then I get to 48, 49, and 50. If I turn around from that point and then add the rest of the numbers, 51, 52, 53, etc., to 98, 99, and 100, if he groups the numbers in this way, it turns out that each pair of numbers vertically has the same sum. 1 plus 100 is 101. 2 plus 99 is 101. And 3 plus 98 all the way through. 48 plus 53, that would be 101. 101 and 101. Oops, 101. Not suddenly 100 there. Typo on my part. Okay, so, oops, there was another typo there. 101. All right, so every single pairing of numbers there added up to 101. And he has 50 of these pairs because he's got the numbers up here from 1 to 50. And so what this really turns out to be is just 50 pairs of 101, and then it turns into a real quick little multiplication problem. So 50 times 101 turns out to be 5,050. And that was the answer that little Gauss brought up to his teacher, 5,050. And that turns out to be the sum of all these integers. I know, right? Wow. So little Gauss was brilliant. I am amazed by this story. Yeah, I hope this really happened because this is pretty cool. And yeah, we all get to reap the benefits of this. Let's see, how old was he when he did this? I'm not entirely sure. The story is like elementary school aged, like maybe third grade or something like that, since obviously he had learned to multiply at some point. But since he was such a dang little genius, I mean, he might have been younger than that. But yeah, so it's pretty neat. Like I picture like a little, I don't know, 8-year-old or something going up with this. Yeah. OMG, I was playing with Barbies back then. Yeah, little Gauss was playing with the numbers from 1 to 100. Pretty amazing. Yeah, I know I would have been amazed. Like crazy. Yeah, so this is a really cool story. I love this one. But yeah, I think Gauss also expanded on this later and just took this into a general summation because we have this formula now for the general sum of the first n integers. So you can take little Gauss's idea here and expand it for any sum of integers. Like it doesn't just work for 100. You could do pretty much whatever value. Someone get him some Legos so he doesn't have to play with numbers. Nice. Yeah, back in the day, they didn't have video games, so they had to do stuff like this. um, but yeah, for our general sum of the first n integers, we're going to take little Gauss's idea here and do a summation from k equals 1 to just n, make it generic now, and keep the formula k. So you're just going to add together 1 plus 2 plus 3, and then you're going to get up to that finishing index of n. As we're approaching it, it'd be like n minus 2 plus n minus 1 plus your value n. All right. And if n is an even number, little Gauss's idea applies directly because, since 100 is even, he was able to split this into two nice even groups of 50 numbers each. But it turns out you can actually still use that same type of concept even with an odd number. All we got to do then, thanks again, Gauss, probably, is to do half of the sum of double those numbers. So you add 1 plus 2 plus 3 all the way up to n, except then you do it twice. So plus 1 plus 2 plus 3 plus ... up to n. So if you add all the numbers you want twice and then you cut the result in half, you'll get the sum of your first n integers. Pretty clever. But that gives us two nice groupings to work with, just like little Gauss. All right, so there's our two groups. Each one of them just goes from 1 to n. And so we're going to have, for this portion alone here, our two groups. I'm kind of going to put some big parentheses here, I think. we'll have our 1 plus 2 plus 3 all the way up to n minus 2, n minus 1, and n. And then just like little Gauss, we're going to turn around and add our second group of numbers. So plus 1, plus 2, plus 3, dot, 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 up to n minus 2, plus n minus 1, plus n. Okay. So when we do that, we can add up the different pairs of numbers little Gauss style. So we take 1 plus n and get, well, 1 plus n, or n plus 1. We'll write it that way. And then our second little group here, 2 plus n minus 1, or n minus 1 and then add 2 to it. That would also give you n plus 1. And same thing here. All right. N minus 2 plus 3 adds up to n plus 1. And then the same exact thing happens down here. You get n plus 1, n plus 1, and n plus 1 for all of those pairings of numbers. Okay. So we've got, let's see, how many groups of these do we got? We've got n groups of these n plus 1 terms. So this all, just like little Gauss, turns out to be a multiplication problem. We're going to multiply our number of groups times the sum of each group. So we'll have our n groups times n plus 1. And so when we multiply that by a half, we end up getting our general summation here. So the results here, excuse me, I gotta shrink this down real quick so I can fit our formula in here. That kind of, yeah, expanded a bit there. All right. So yeah, our formula for the summation of the first n integers is just going to be 1/2 of n times n plus 1, or as we more commonly write it, n times n plus 1 divided by 2. And there we go. And that actually works out for little Gauss's formula as well from his problem. His n value was 100. So he had 100 here times 101 and then divided by 2. Well, 100 divided by 2 gave him that 50 right there. So his formula from grade school still works out with this general sum as well. So yeah, this is the sum of the first n integers. This is a good one to know. And frequently in future videos, I will probably refer to this as the little Gauss formula, just because I love that story so much. But yeah, that's our general sum. Now, there are some other additional sum formulas that you might find useful. Don't worry about memorizing these next two. Usually I do like people to memorize the little Gauss formula just because it comes up so much in this chapter. But yeah, that would be good just for this chapter. It'd be a nice choice. But yeah, these additional ones, don't worry about memorizing these, and these do not have quite as nice and neat of a proof as little Gauss's formula. If you want to look at the proofs, they're in the e-text in the back in Appendix 2, but they're significantly longer and they don't have a fun little story with them, so we won't do them on video here. But these are the sum formulas for the sum of the first n squares. So the sum from k equals 1 to n of the formula k squared. These all have a fairly similar look to them. It starts out with n times n plus 1 times 2n plus 1 divided by 6, which feels a little bit random, but again, you can check out proof in the appendix. I won't make you prove this one at any point. All right, and you don't have to memorize it. If you need it on a test, I'll give it to you. And then the other one is for the sum of the first n cubes. So summation from 1 to n of k cubed. Strangely looks like little Gauss's formula, n plus 1 over 2, but then the whole entire thing gets squared. And again, that is kind of weird feeling. You might see this written sometimes as n squared, n plus 1 squared over 4. That's just applying the square to everything inside. But yeah, if you need that one on an exam, I'll give it to you as well. But there we go. There are all three of our main summation formulas. And yeah, we'll need these definitely in the next section. So that will be a good thing to have.